Hello, thanks for joining me again for another video on integration, the fourth one of the series on this chapter for Year 13's Edexcel A-level course. So this part is looking at a concept known as the reverse chain rule, and although the book explains it in, as ever, a decent way, I do like the books, they tend to explain it using the idea of the reverse chain rule, so looking back at something to think what it could have been before the function you're trying to integrate was integrated. So essentially thinking what could the integral have been and then working back from that. So it's quite an advanced skill, I think, and something which I believe should be built up to. So I'm going to explain why I teach it my particular way within the video, and I'm also going to link you to an extra video should you wish to think about why a bit more, why I'm so into this particular method of use substitutions instead. Anyhow, let's get warmed up with a couple of examples. So the first set are identities, which are notoriously tricky for some, not always obvious, and question 2, a mechanics question, 2 parts A and B. So pause the video here, try them now, and when you're ready to see the solutions, press play, and fingers crossed yours should match mine. Right then, so let's have a look at these identities for warm-up question 1. So first of all, we have to prove the identity that sec squared x minus cosec squared x is equivalent to tan squared minus cot squared. So let's make the left equivalent to the right. So I'm going to write this out as it stands. So I've got sec squared x minus cosec squared x. And down here, I'm just going to put a little reminder for you, should you have forgotten the identities. But importantly, there's 2 key identities to remember in order for us to get this solved easily. The identities are that 1 plus sec squared, sorry, 1 plus tan squared I should say, 1 plus tan squared x is the same as sec squared x. And the second one we're going to use is that 1 plus cot squared is one and the same as cosec squared x. So that means we can rewrite sec squared and cosec squared in terms of both tan squared and cot squared. So sec squared I can write as 1 plus tan squared x, like so. I want to put it in brackets to emphasize to anyone maybe marking your work that you're just using this and you explicitly know that sec squared is 1 plus tan squared, so it can't hurt to make it obvious to an examiner. And minus cosec squared x, well, cosec squared is 1 plus cot. So then just simplify, you'll notice that the 1's will cancel, so 1 and that minus 1, so that's just going to give us what we need, and then we're done. So that goes down to, simplifies down to, tan squared x minus cot squared x as required. So let's have a look at part B now. So part B, we need to prove that cos x over 1 plus sine x plus 1 plus sine x over cos equals 2 sec x. These are the restrictions on x to make sure that the denominator isn't going to ever equal 0, so that this will actually work. Okay, I'm just going to give a little hint here. If you've got a fairly awkward or possibly awkward identity, and you fear that you're going to have to write sine, cos, tan all the time, what you could do is just say at the top of the page, just let S be sine x, C can be cos. So just note that, and then we can work a bit quicker. So the left-hand side, we've got cos, just going to put C, over 1 plus sine, and then 1 plus sine over cos. So our target is to have something which isn't a fraction, and certainly not 2 fractions. So let's start by trying to combine these 2 fractions into 1. So always be thinking about what your target is, and try and manipulate each stage so that each step you take, you get 1 step closer in form to the right-hand side you're aiming towards. So how can I get these as a single fraction? Well, I need a common denominator. So what I could do here, I could multiply numerator and denominator of this one by c, cosine x, And this one here, I could multiply numerator and denominator by 1 plus sine. So if we do that as our next step, that's going to give us cos squared on top for the first bit. On the bottom, we're going to have cos multiplied by 1 plus sine. And for the second fraction, because we're multiplying by 1 plus sine squared, the top will just become 1 plus sine squared, of course. And the bottom, again, cosine multiplied by 1 plus sine. So now I can combine these because I have a common denominator, which is what we wanted to have. So cos squared, just leave as cos squared. 1 plus sine all squared becomes 1 plus 2s plus s squared. And now just let's pause for a second and have a look what our target is. Our target is 2 sec x. So 2 sec x, I'm just going to doodle it here. I'll clear some space in a moment. 2 sec x, just bearing in mind what we're aiming for. That's just the same as 2 over cos. At the minute, I've got 2 over cos brackets 1 plus s. So if I could do this just for a second, because obviously 1 plus s on the top, 1 plus s on the bottom would cancel. My bottom is already fine. So if I can change this top into 2 brackets 1 plus s, then I'm good. So that's just me thinking out loud. Always be thinking how I can get with each step close to the target. So at the minute, that needs to become 2 plus 2s, which can then factorise into this. So I've got the 2s. What I need here is the 1 plus c squared plus the s squared to somehow become 2. So essentially what I need to do here is to use the identity that cos squared plus sine squared equals 1. So that's actually easy to do because I've got a cos squared and a sine squared. So I can just replace that with an extra 1 plus the 1 plus 2s I already have, all over cosine multiplied by 1 plus sine. So then, of course, that's just obviously 2 plus 2s. So I can factorise out the 2 to get 1 plus s. On the bottom, cosine multiplied by 1 plus s. And then, obviously, we can hopefully now see that the 1 plus s on the bottom will cancel with 1 plus s on the top. So I'm just going to have 2 over c, where c, of course, is cosine x. So just return to what we defined it as. By the way, doing sine x as s, cos x as c is completely optional. You don't need to do this. It's just my suggestion because I think it saves time. And 1 over cos is defined as sec, so therefore we're done. So that becomes 2 sec x, which is the right-hand side, so we've reached our target. Final one, part C, we have to prove that sine 2x minus tan x is tan x cos 2x. And again, this restriction is just making sure that the denominator in the tan isn't going to ever be 0, so it doesn't blow up. So don't get too hung up about that restriction. Let's just manipulate the trig identities so we can get the left to match the right. If you wanted to do, you could do the right matching the left, but generally go from left to right. So, the left-hand side, I've got sine 2x minus tan x. So I'm going to change this. I'm just thinking, there's no sine 2x on the right, so I need to get rid of sine 2x and probably just replace it in terms of sines and coses. Then I can maybe get a tan back again, because I don't have a minus tan there, so maybe I can get tan in a different form. So sine 2x, I'm going to say is 2 sine x cosine x. And tan x, I'm just going to rewrite as sine over cos, just so I can picture better what I'm doing. So I've got sine x in both terms. So what I'm going to do now is going to factorise out the sine x. So I've got sine x, open brackets, 2 cos x minus 1 over cos x. We've factored out the sine here, so we don't need the sine again, so it becomes just minus 1 over cosine x. Our target is a product of two simple-looking things, so right now this second one isn't looking simple. I could simplify this by getting it into a single fraction with a common denominator of cosine x. So I'm going to multiply cos x by itself and divide by itself. And then this will give me 2 cos squared x over cos x, which I can then combine into a single fraction. So my next step is to say sin x, and in brackets 2 cos squared x minus 1 all over cos x. Now I can rearrange this and put the sine over cos here. So rather than divided by cos here, I can put sine over cos there, and that'll give me the tan, which is getting closer to my target. So if I just rewrite it as sin x over cos x at the front, then multiply by 2 cos squared x minus 1, but I've got the tan x here, which is good. So the clue is, can I convince an examiner, and myself of course, that 2 cos squared x minus 1 is the same as cos 2x? So if in doubt, I'm just going to show you. So cos 2x, using the compound angle formula, double angle formula I should say, is cos squared minus sine squared. So to prove that it's the same as this, I don't want anything to do with sine squared. So cos squared x, using the identity that sine squared plus cos squared equals 1, then rearranging, I can see that sine squared is the same as 1 minus cos squared. So cos squared minus cos squared, of course, gives us 2 cos squared x minus 1. So hopefully that shows clearly that this bit here is the same as cos 2x. So final step, sine over cos we can say is tan x, because it is, and 2 cos squared x minus 1 is of course cos 2x. So we've shown these identities to hold. Let's have a look at the mechanics warm-up question, question 2. Quite a lot of information to digest here. So we have a uniform steel girder, keyword uniform. So in fact it's so important this, I'm just going to highlight what this means. So uniform means centre of mass is at the middle. So it says it's mass 40 kilograms and length 3 meters. So because it's uniform, that means its centre of mass is going to act halfway along 3, which is 1.5. So there, that's 1.5. I'm going to call that 40g, acting downwards, because 40g is of course its weight. If its mass is 40. Make that line longer so I'm not cramping all the information in one. That's 40g. And I'll highlight on the actual distance, which is 1.5 here. Next, it says it's freely hinged to A at a vertical wall. So it's held there, this girder, and it's supported in a horizontal position by a steel cable attached to the girder at B. So this is the cable as such. The other end is attached to C, vertically above the wall, and angle ABC is alpha, where tan alpha is 3/4. So this is going to be something we can work with. So what I'm going to say we do here is to actually consider what sine and cosine alpha will be, and that's going to help us when we come to resolving into components. So of course that's alpha. So I put alpha there. Tan is defined as opposite divided by adjacent. So imagining a right-angled triangle, alpha the opposite side and adjacent is in the ratio 3 to 4. Using Pythagoras, the hypotenuse of this would therefore be the square root of 3 squared plus 4 squared, the square root of 25 in other words, which is 5. And so from this we can deduce sine and cos alpha in terms of exact fractions. So I'm just trying to make this a bit neater, bear with me please. There we go. Just sectioning it out of the way so it's not going to interfere with our main working. There we go. So from this we can see therefore cosine alpha is adjacent divided by hypotenuse, which is 4/5, and sine alpha is opposite over hypotenuse, which is 3/5. In addition to the other information, we have a load of mass 60 kilograms suspended by another cable from the girder at the point D. So this is the load here. And A to D is 2 meters. So that's been labelled on nicely for us. So I'm just going to call this weight here, acting down, 60G. What else are we told? The girder's in equilibrium, so forces will balance. The girder is modelled as a rod, and it's a uniform rod. The cables is light, inextensible strings. So we can finally get on to answer the question now. Show that the tension of the cable, BC, is 980 newtons. Well, the tension of the cable is obviously going to act up and away from the beam. So tension never acts towards something. That's called a thrust if it does. So if I label on the tension here, and I'll colour code it so it's not blended in, so it's a bit clearer. So if I call this T, like so, then I can resolve T into components T cos alpha, going along and into the wall if you like, and T sine alpha going up. So if I just put these in a dotted line like so, so going that way will be T cos alpha, and cos alpha of course is 4/5, so T times 4/5, that's just 4/5 T. And going upwards is going to be the sine component of T. So T sine alpha going up, and that's the same as 3/5 times T. So, show that the tension of the cable BC is 980 newtons. But of course, if you just read on and look at part B, there's going to be a reaction on the girder at A, and of course there will be. So there's going to be a force acting at A there. So we can't just consider forces up and down acting on the girder, because there's an unknown force here, the reaction. But because the unknown force is acting at A, what can we do in terms of mechanics so we don't need to concern ourselves with a force acting at an unknown point? We can, of course, take moments about that same very point. So my suggestion here, in fact, what we sort of must do, is take moments about A. So we're just considering forces acting upon the girder. So going clockwise, acting this way round from A, we've got 2 weights. So we're going to have 40G, which is the force multiplied by the distance of the line of action of the force from the pivot, which is 1.5. So 40G times 1.5. Then, of course, is 60G weight. And that's acting at a distance of 2 meters. That's going to be equal and opposite to the anti-clockwise forces acting on this girder relative to the pivot A. So the only other force acting which doesn't go through A is this tension, but we can think of this tension as being resolved into horizontal and vertical. The horizontal component will go right through the pivot, therefore has no turning force relative to A, but T sine alpha will. So I'm going to call this T sine alpha, which is of course 3/5 t, multiplied by the distance of this arrow from A. So of course the distance again is just going to be 3. So simplify, 40g times 1.5 is 60g. 60g multiplied by 2 is 120g. And 3/5 times 3, of course, is 9/5. So that's going to give us 9/5 over t, or I can call it 90 over 5. Doesn't particularly matter. So, next up, 60g plus 120 is 180g. Gives us 90 over 5. If I then multiply both sides, divide both sides by 9/5 to get rid of that and just get t on its own. And over here, divide by 9/5 as well. You can see that therefore t must be 100g. Basically, divided by 9/5 is the same as times by 5/9. So 5/9 of 180, 1/9 of 180 is 20, so 5/9 is 100, so therefore 100g. Of course, we know that g to 1 decimal place is 9.8, so t is 100g, which means 100 multiplied by 9.8, which is 980 newtons as required. For part B, we now need to find the magnitude of the reaction of the girder at A. So there's going to be some reaction on here. We don't really know if it's going to act up and away or down and away. My hunch is it's going to be acting up slightly. But how do we know? Well, now we know what the tension is, we can now consider forces acting vertically on A. So just considering for part A, forces acting up and down. So forces going down, we've got 40g and 60g acting downwards. Forces acting up, I'll let myself a little space because I'm not sure if, of course, this R force will have to act up or down, but we can work this out now. The force going up is T sine alpha, so that's going to be 3/5 of 980. So 40g plus 60g is 180g, which, sorry, is 100g, which is the same as, of course, 980. Over here, we've only got 3/5 of 980, so we need more force going upwards to make it balance with the weights going down here. So therefore, we can deduce actually that this reaction acting at A must be going slightly up. So if I just call the reaction R like so, acting at an angle theta up from A. So the force acting up in terms of R must be going on this side, because obviously that's 100g, this isn't quite, so it needs to be an upwards force. So the component acting up, if it's acting at an angle theta to horizontal, is going to be R sine theta. But how do we know what theta is? Well, we can work this out, which is going to take a bit more time. One thing we could do, though, is just rearrange this equation. So from this, if I just subtract 3/5 of 3/5 of 980 from both sides, rather, I can see that R sine theta must be 100g, which is 980, minus 3/5 of 980. That's going to give me 2/5 of 980 left. So I can just work this out here. So 2/5 of 980, 0.4, is 392. And then we can actually think about forces horizontally, relative and acting upon the girder. So we can see here T cos alpha, this what's it called now? The cable has a component pushing into the wall, T cos alpha. So therefore R pushing the other way, which would be R cos alpha, must be equal and opposite to R cos theta, I should say, must be equal and opposite to T cos alpha. So that's going to be equal and opposite to 4/5 T. But we know what the tension is. The tension's 980. So 4/5 of 980. Let's just work this out. Well, that's 2/5. So if I double that, 784. And we need the magnitude of that reaction. So we've got our components. Now we can just think about it in terms of right angled triangle. So what we had was R going upwards, like so. But we just worked out R sine alpha and R cos alpha. I keep saying alpha, I mean theta. Apologies. So that was theta here. R sine theta we got was 392. So that bit here is 392. And our cos theta is 784. So then using Pythagoras, so R squared is going to be these two squared and added. So to get R, we just square root that. So therefore, R, or the magnitude of R I should say, is going to be the square root of 784 squared plus 392 squared. So 784 squared plus 392 squared. That gives us two significant figures, 877. So 877 newtons. So now done those warm-up questions, let's get to the main bit where we're going to consider how to integrate using the reverse chain rule, or as I would call it, a U substitution method. So today's main focus is integrating expressions of the form kf-x either divided by f of x to the power n or multiplied by f of x to the power n. So essentially, these two things, although they look different, are one and the same. If n is a rational number, for example, if n were to say be -2, I could write this as kf-x f of x to the -2 as a product, or I could write it as kf-x all over f of x squared. So if you're thinking why have I wrote it in two different forms, I'm just trying to emphasize and really drive home the point. It can look in like two different things, but actually it is the same form in disguise. As we've seen already, U substitutions, if you use them right, of course, can simplify integrals involving a function of a linear function, ax plus b. We can also use U subs to great effect when integrating this or that, like I've said in the title, which these two things are essentially both the same. In each of these two cases, what we do is we set U equals f of x, we rewrite dx in terms of du, then integrate in terms of U. Why it works, I'm not going into huge detail. Hopefully with the examples you'll just see that it does, but if you want a bit more of a robust sort of way of convincing you, I've put this link here which explains it slightly in more detail. But for the sake of brevity today, I'm not going to get into the whys and hows, just more so the application, the doing of it, and solving the problems. But if you do want a bit more exploration in terms of why it works, I've put like a tiny bit of light touch algebra in this link, so hopefully you can see a bit clearer why it does work. And so this link is just there to convince yourselves. It's optional, but again, if you're curious, that's never a bad thing. Check it out if you'd like. So apart from that, let's move on and actually apply this. My key take-home point though, before we begin, is this method, in terms of spotting when to use it, you're going to be looking for essentially a product or a quotient expression where you've got a function to some power. The power might be 1, and you can also spot within the product or quotient that also the derivative, some multiple of a derivative, is being multiplied by the original function, which is to a certain power. It makes more sense when you actually apply it. By the first 4 or 5 examples, it should click in. So let's have a look and get started. First of all, integrating kf dash x all over f of x to the power n. So how does this work? The first one, we've got 4x cubed all over x to the power 4 plus 3 dx. So the key spot here is, if this is f of x, and this has not been raised to any power, what would happen if I differentiated x4 plus 3? Well, x to the power 4 would differentiate to 4x cubed. So this is one of these forms where it's f dashed x over f of x to the power 1, essentially. And so and k in our case is 1, because 4x cubed is the exact derivative of x to the power 4 plus 3. So that's why it works. So let's use our u as f of x, which is x to the power 4 plus 3. So set u, like so. We then take du by dx. So differentiating with respect to x will give 4x cubed. So therefore, dx, rearranging to get it in terms of du, dx is going to be du divided by 4x cubed. So we can switch this for that, and also u, which is 4x plus, x to the power 4 plus 3, we can replace here. So let's transform the integral. So what we're going to have now, in terms of u, we've got 4x cubed on top, divide by this, which we've termed to be u. And instead of dx, we've now got du over 4x cubed. So hopefully you can see here, we're going to have the 4x cubed here, cancelling the 4x cubed there. U, of course, is x to the power 4 plus 3, and du over 4x cubed was just dx. So now we can simplify this, and I think this is quite satisfying, to be honest. That just becomes 1 over u du. That we should know is going to go to ln mod u plus c. Then put in the original variable, which of course was in terms of x. That gives us ln mod x to the power 4 plus 3 close plus c. Part B. So can we see anything which differentiates plus or minus a constant to the other thing? Well, if I were to think of differentiating the bottom thing here, 3 would disappear, 2 sine x would differentiate to 2 cosine x, which is just some multiple of the numerator. So again, that's our clue. We can use this u-sub technique. So I'm going to call our u 3 plus 2 sine x. So if I set u as 3 plus 2 sine x, then differentiate u with respect to x, that'll just give me, of course, 2 cosine x. Rearranging to get dx in terms of du, dx will be du all over 2 cosine x. So if we now transform our integral using our u sub, cosine x, I can leave as cosine x for now. This we said was u, which is no problem. And dx we're going to replace with du over 2 cosine x. So to explain what's happened there, I've replaced dx with du over cosine x, and of course 3 plus 2 sine x we subbed as u. As you can see now, hopefully again, we'll have some nice cancellations. Cos x on top, cos x on the bottom. Be careful not to cancel that 2. This will now give us a much easier integral to solve. We've got a 2 on the bottom, which gives us a half integral, once again, of 1 over u with respect to u. So we're going to get a half ln mod u plus c. And again, subbing in what u was, go back to the original variable in terms of x, we have half ln mod 3 plus 2 sine x plus c. Part C of this type, again, we're just inspecting if we can see what the denominator would differentiate to. So for this one, if I were to term u e to the x plus 8, 8 would differentiate to nothing because it's just a number, it's a constant. E to the x differentiates to itself, which is e to the x, which is just some multiple of 4e to the x. So the derivative of the denominator is just essentially a quarter of the numerator. So that's our clue that we can set u to be this function here. So u, we're going to say, is e to the x plus 8. Differentiate that to get du over dx, which of course is just itself. So now we can say dx must be du over e to the x. We now transform the integral using the sub. So on the top we have 4e to the x. On the bottom, ex plus 8 we said was u, so we've got u squared there. And instead of dx, we're going to have du over e to the x. So ex plus 8, that is u, and dx, we can say it's the same as du over e to the x. So again, we can simplify this quite a lot. So the e to the x will cancel on the bottom and the top, and so we're going to be left with, got that factor of 4, which I'll take to the outside. 1 over u squared now, I'm going to write this as u to the minus 2 du, because I think, generally speaking, unless it's 1 over u, where you can spot it's going to be in terms of ln, generally speaking, writing a variable in terms of index form is easier to see and easier to know what to do in terms of integration. So that's going to give us 4, add 1 to the power, so I get u to the minus 1, and divide by the new power. Anything divided by minus 1 is the same as multiplying by minus 1, so I'm just going to get minus u to the minus 1 there, plus c. Finally put in what the actual u was, so it's minus 4. U to the minus 1 means 1 over, so it's 1 over u, which we said was e to the x plus 8, plus of course c. So we've done a few where that's of a type where it's looking like a fraction, where the numerator is some multiple of the derivative of the denominator. The other form, I think, is actually easier to spot. So let's try the other form, where it's the same thing but looks like a product. So integrating these. So I've got sine x plus 1 cubed. Again, generally speaking, with u subs, you're always wanting to sub out the harder sort of looking thing. Clearly, sine x plus 1 and then cubing it is more awkward than cos x. So could a u sub for sine x plus 1 be useful? Well, yes, it could. The reason being because sine differentiates to cosine, and so this here is some multiple of the derivative of that, where the multiple is exactly 1, fortunately. So we're going to set u, in this case, as sine x plus 1. We can then differentiate. So du by dx, sine differentiates to cos. The 1, of course, will vanish. We can now get dx in terms of du. So dx is going to be du all divided by cosine x. So now we can transform this using the substitution. So we have cosine x multiplied by u cubed, and dx becomes du all over cosine x. Once again, I'm hoping you can see that we're going to get some cancellations. Cosine x and cosine xi will cancel. So I'm just going to have the integral of u cubed du. So add 1 to the power, divide by the new power. That gives me a quarter u to the power 4 plus c. Sub in what u actually was, we've got a quarter sine x plus 1 to the power 4 plus c. Part B. Again, if we have a look at x squared plus 5, x squared plus 5 would differentiate to 2x. 2x is just double some constant multiplied by that. So again, we know now we can use this u sub technique. So set u as this inner function within the brackets x squared plus 5. Differentiate that. du by dx will just become 2x. So therefore, dx is going to be du over 2x. Transform the integral. So then we're going to have the integral of x. This is u, so it's going to be x u to the 6 dx, which we're going to say is du over 2x. I always like a bit of colour coding. You know me by now, I'm hoping. So that x will cancel here, and an x will cancel there. Don't cancel the 2, of course, so just be careful when you're just cancelling with lines. Don't overly do them. So this is going to give us, we're dividing by 2, so I'll put that half on the outside, and then we're just going to have u to the power 6 du. So now that's going to become half. Increase the power by 1, then divide by the new power. So that's going to become u to the 7, divided by 7. So it's 1/7 u to the 7 plus c. Half of the 7th is 1/14. So finally we get 1/14 of u, which was x squared plus 5 to the power 7 plus c. Finally, for question 2, part C, we've got cosec 5x cot x all over 8 with respect to x. So the first thing I'd suggest we do here is we just rewrite this, take out the 8 straight away, and just call it cosec 5x cot x dx. You don't have to, but I think it's easier and neater taking out the constants first. So this is obviously slightly trickier. It's not as obvious to spot what we need to do here. The clue is, generally with u-subs, you're subbing into something more awkward. So the more awkward thing is obviously the cosec, which is to the power 5. So use your formula book, have it by your side, and your hunch should be, maybe u would be worth putting as cosec x. So let's try that and see what happens. So let u be cosec of x. Dig out your formula book, or hopefully just know or remember that if you differentiate cosec, if we do du by dx, that's going to give us negative cosec times cot. Okay, so this bit here, don't like that green, it's a bit too unclear. So here, if you're not sure, I'm just going to put check formula book. I'm not going to go into detail. As I say, the main focus for me today is just showing you the application of this. So if you're not convinced, it's in the formula book. So we can then rearrange to get dx in terms of du. So dx is going to be du all over minus cosec x cot x. Now spot here, when we differentiate, we also have u within the derivative, and so just be careful how you rewrite this integral. So we're going to transform it, we're going to be a bit careful. Okay, so I'm going to have, obviously, the 1/8 on the outside. Now dx, I'm going to write last, so we can hopefully see what to do. So I'm going to put over here, oops, bit of a pen dribble. So that times du over minus cosec x cot x. The reason I'm doing this is because just have your eyes always on what you want to cancel. So obviously that cot x will cancel that cot x, but I need to cancel a cosec x. So I'm not going to write cosec to the power 5. Obviously I'm calling u to be cosec x. So what I'm going to do here, I'm going to write it as u to the power 4 times an extra u. So u to the power 4 times u. So I've got an extra cosec x left now, which can now cancel off after. So I'm going to call this u to the power 4 cosec one of them. I'm not going to leave myself enough space yet again, so if I just move that here for a second. So I've got u to the power 4 cosec x cot x, and then what I'm going to do, I'm going to obviously replace dx in terms of du. Sorry for being slightly unneat, folks. Sometimes my mouse can be. So u to the power 4 times cosec x squared. Just take a moment to convince yourself that is u to the power 5. I've just partitioned it so that one bit here will nicely cancel with that. You need it to cancel, otherwise you're in trouble. So cosec will cancel with a cosec there, and also I'm going to have that cot cancelling with that cot. But don't forget about that pesky minus. So I'm going to get minus 1/8, then it's going to be the integral of u to the 4 du. It's got minus 1/8. U to the 4 would integrate to a fifth u to the 5, of course, plus c. Finally, just simplify. 1/8 of a fifth is a 40th, so it's minus 1/40th, because of that minus sign. U, which is cosec x to the power 5, so it's going to be cosec 5x plus c. Let's now do one where we're going to have to consider definite limits. So question 3. Given that from theta down to 0 of 5 tan x sec 4x dx is 15 over 4, where theta's between 0 and pi over 2, find the exact value of theta. So my suggestion is to ignore the limits for now, just do one thing at a time. Can this integral here be simplified? So if I just say it's 5, take the 5 to the outside. I need to integrate tan x sec 4x dx. So if I were to set u as sec 4x, sorry, sec x on its own, I should say. So this time what I'm going to say is let u to be sec x. Formula book here helps again. This one, if I do du by dx, that's going to become sec x tan x. So therefore dx, rearranging in terms of du as we tend to do, hopefully you'll see a bit clearer now what happens each time. We get du all over sec x tan x. So clearly I want a sec to cancel here, and so what I want to do now, I'm going to rewrite this I could rewrite it later. If I rewrite it as 5 tan x sec x, and really make an emphasis that I'm just doing sec cube x dx on the outside, that might make it easier for us, and in fact it definitely will do. Okay, so u is sec x. So we can now transform this integral. So 5 on the outside, integral of tan, I'm going to rewrite sec as sec to power 4 as 1 sec times sec cubed, like I've done here. So I've got 10x sec x, but just remember that u is sec x. Sec cubed x I can rewrite as u cubed. Brackets are sort of optional here, just to make it clearer perhaps. And then dx I can now replace with du all over sec tan. So tan cancels with tan, sec will cancel with sec. So that's therefore going to give me just 5 lots integral of u cubed du. U cubed integrates to a quarter u to the 4, and so that gives 5 over 4 u to the 4 plus c. Remember what u actually was. U, we said, was sec x. So we're going to have 5 over 4 sec to the power 4x plus c. So that's the first bit done. I'm just considering it all indefinitely. So this bit here is going to be very useful, because now we've got definite integrals to consider. So therefore now, in between theta and 0, 5 tan x sec 4x dx, between limits, obviously we don't have the concept of integration. The concept of integration would obviously cancel out each time. So what we're going to do now we've got this expression, we can use it. So it's 5 over 4 sec to the 4x between theta and 0. So now just put in the actual value theta. So that's going to give us 5 over 4 sec to the power 4 theta. Now if I put in 0 for x, sec x is 1 over cos x. When x is 0, cosine is 1. So 1 over 1 will be 1. 1 to the power 4 is going to be just 1. Use your calculator if you don't like that thinking. But essentially all you're going to have there is just subbing in 0. This becomes exactly just 5 quarters. So minus 5 quarters. And we're told that's equal to minus 15 over 4. So we set this result to be equal to 15 over 4. We can now progress and hopefully solve. So I'm thinking, I don't like these fractions, let's just multiply them by 4. You can do it in different ways. If I just times everything by 4, I'm going to get 5 lots of sec 4 theta minus 5 equals 15. Add 5 to both sides. 5 sec 4 theta is 20. Divide by 5. Sec to the power 4 theta is going to be 4. Now, if I work out what sec theta is, basically sec theta, because I'm taking a even fourth root, so square root or fourth root or sixth root, I need to consider plus or minus the fourth root of 4. Now, the fourth root is the square root of the square root. So if I just term this as plus or minus the square root of the square root of 4, so it's plus or minus the square root of the square root of 4, which is 2. So I've just got plus or minus root 2, of course. So now that's sec theta. So I want cos theta really, because we're more familiar with cos. So cos theta is 1 over, plus or minus 1 over root 2. Then if I were to rationalise the denominator, times both top and bottom by root 2, you get plus or minus root 2 over 2, basically plus or minus a half root 2. So this should be familiar to us. This is one of these exact values for theta. So half root 2. Again, if you're not sure, what we can do is just use a calculator if you really want to get the principal value. So theta. Now, if we're integrating, you need to have this in terms of radians. So just to remind you. So we're going to press menu, so shift menu, angle unit number 2, we're going to go for radians option 2. So I want to do cosine minus 1 of a half root 2. So if I just put in here root 2 over 2, if ever you forget, a quarter pi. So that's the only one we're going to have. The plus or minus that option isn't in this range. So the only answer we're going to have which is valid is going to be pi over 4 or a quarter pi. So I'm going to say theta is a quarter pi. If you put pi over 4, that's equivalent. That's just the same thing. It looks a bit different. And that's it. Now the only thing for you to do is to practice, practice, practice. On that note, if you could turn to page 302 to 303, exercise 11D in your beautiful blue books. You could do question 1 as well if you wanted to. I think question 2 goes through that quite well anyway. So try question 2 all the way to the end is my suggestion. You know the drill by now. If you get stuck, check the solutions or ask me. If you're still not sure, ask me again or go to a help session. And don't give up, because integration is so crucial for success. Take care, thanks for listening, and I hope to see you all soon.